So good afternoon. I hope everybody had a good lunch. Topic of my today's presentation is LEESA, which is a XML processing language in C++ embedded language. It's not a XML parsing library in not even close. So just to give you a heads up, so I'm going to steer away from all the parsing issues, all the stuff like that. So it was 2008 when I started working on LEESA. In the context of data binding, I'm going to tell you in detail what data binding is. And by the way, I just realized that like about 2 days I'm here, I did not feel the altitude change, and because of that, but I think while talking loud, like a big audience, I think I'm quickly running out of breath. So that might happen by second slide. I don't know. So yeah, I was a PhD student in Vanderbilt University. I have since graduated and I work at Real-Time Innovations in California. So this particular work is, I took it from 2008 and now it's 2011. It started in context of data binding and moved towards XML data binding particularly. The way it started was a really modeling tool that I did research on. From the institute where I did finish my PhD. So let me begin with a question. So raise your hand if you think XML processing as such is just a lot of burden. You feel you write too much code to get too little done. Or if you are absolutely happy with your XML technology and you feel XML is just another form of poetry, raise your hand. Okay, so nobody here thinks XML is so wonderful. That's great. Hopefully, this presentation may make you feel like you can in fact write XML processing, which almost looks like poetry. But that's a hyperbole. But let's go ahead. So my goal today is to basically take you, if you feel like this, to here. Let's see how I accomplish that. So I feel XML, if you look at the number of technologies that are available today for XML processing, there are just enormous number of technologies that you can use. You have open specifications, you have so many books written on it, you have open source libraries, you have commercial libraries, you have academic researchers working on it, you have industrial researchers, so many smart people working on trying to get XML programming right. It's almost like deceptively simple. It looks kind of simple, but it's not. Why do you need so many technologies? And so I think the reason lies in it's actually a full-fledged paradigm, like functional programming, object-oriented programming, procedural programming. If you consider XML as a full-fledged paradigm, then I think you'll find why it's so complicated to get it right when particularly you deal with complicated XML processing issues. So I have picked up on certain idiosyncrasies of XML programming. If you look at the type system, there are regular types, anonymous complex elements, and repeating subsequences. These are kind of esoteric features in XML. And I don't expect you or anybody to understand what those are, but they are kind of eccentric things, and they are not found easily in object-oriented languages. Then you have XML data model, which is standardized as information set, in short, info set. Those are basically elements that you are probably familiar with, elements, attributes, text, comments, and processing instructions. These are the things you can have in an XML document. And with this data model, you can have your own application-specific data model, and to define that, you have schema languages. So you have XSD, DTD, RelaxNG. These are all schema languages to define your application-specific model in terms of these kind of very general XML things. Once you have your data model and schema languages, you have your processing languages, particularly for XML. XPath, XQuery, and XSLT are particularly geared towards XML programming. And obviously C++ is not here because it's not specifically for XML. And over the years we have developed a lot of idioms and best practices for how to deal with XML. I'll be talking about XPath most of this, rather the first half of this talk. So I picked up examples from XPath. So things like child axis, descendant axis, these are that's kind of lingua franca of XML programming. Why am I bringing all these things? You know, it is good to have these things at your disposal when you're dealing with XML. Believe me or not, you know, XML programming is easy if you use XPath XQuery, because it is really meant for it. If you are going to deal with really complicated XML data model, you know, processing instructions maybe, or, you know, namespaces, multiple namespaces, chances are these languages handle it much better than a open source library. Of course, you know, give and take some exactness there. So if you have these things in C++, my belief is you can be very productive in XML programming. So what do we have in C++ today? We have DOM API libraries, event-driven API libraries like SACs. I mean, they are modeled after SACs, which is quite famous in Java. And then we have XML data binding. You generate classes from your schema, and that's what I will be talking about most of the talk today. What about Boost? Unfortunately, as far as I know, today there is no XML processing library dedicated, you know, in Boost. There is Boost XML in Sandbox. I checked last time. It's still in Sandbox. I don't know when that will be accepted as an official library in Boost. But part of the reason why we do not have a dedicated XML library in Boost is XML is just a huge set of specifications. There are already some good XML libraries out there for C++. Then there are encoding issues, round-tripping issues, a lot of things that you have to deal with, and you have to have a consensus in an open environment like Boost. You know, you cannot actually satisfy every single requirement in a library that is for XML processing. That's why, I mean, that's probably one of the reasons why XML programming is itself a paradigm, and you cannot have just single library to solve it all. That's probably an indication why we don't have a Boost XML so far. So XML data binding, yes. This is going to be very interesting because I'm going to say not so nice things about XML data binding, and that should be very interesting because we have in our audience a data binding expert right here, Boris, and he's in the front line. He's already maybe ready with a sword, I don't know. So let's see. I'm going to tell you what are we missing in XML data binding and how we can improve it using the work I have done. So data binding is pretty straightforward. You start with an XML schema. You have an XML schema compiler, and that generates C++ code, header files and CPP files for you. And you write your query traversal, you know, using for loops, whatnot, using that. And you just get your executable, pretty straightforward. And this C++ code is very kind of reflects your XML structure neatly. Parsing and serializing and deserializing XML is already taken care of for you by the generated code here. So it can do validation for you. It can check errors in your XML document and, you know, stuff like that. So this is pretty neat. This works particularly well when you are faced with really large XSD and you have a large schema and about, I don't know, 500 types, 1,000 types. So this kind of approach works very well with that. So here's an example. So a simple, this is going to be a running example throughout this talk. A simple catalog, actually this part C is kind of missing. Okay, so we have a simple catalog, contains one or more books, and books contain name and author, pretty straightforward. And this is the XSD that, you know, or I should say, this XML conforms to this XSD. Which defines how a book looks like. It has element name, price, author contains another name. So this particular example I have created to bring out the essence, the challenges in XML processing. This is extremely simple by any means. You know, you probably don't need XML data binding to process such a simple schema. But there are interesting challenges that I will be talking about even in this particular example. So from this same schema that we saw earlier, you generate C++ classes, and if you see, they kind of map one-on-one. So you have an author definition, I think that's here, and an author has a string name and string country, that's what's here. And then a book contains multiple authors, they make it multiple authors, so that's what it's obtained from here. So it has a name, a price. So pretty straightforward. You have getters and setters for each class that was created, and similarly catalog. So pretty straightforward so far. This is how a typical query kind of looks like when you use data binding. So what it's trying to do is find all names of the authors in the XML that you are parsing. I'm not showing how it's loaded and how it's validated and all that stuff. You start with the root and you write basically 2 for loops. The first one iterates on the books themselves in the catalog, and for each book you basically iterate on all authors, and you push back in a name sequence which you return. Pretty straightforward stuff. So you can imagine if you have more nesting, you will tend to write more nested for loops, or at least separate them out in different functions. This is great, because it kind of speaks the language of your domain. If this is some insurance schema, it will actually say those elements actually. So your code kind of looks like what it's trying to do, and not actually XML nodes and elements processing. You are not going to talk about that. It kind of takes all those XML things away from you. That's the advantage of data binding. So yeah, it is easy to use. It is vocabulary specific. That's what I meant by, if you had a insurance schema, it will have those kind of classes. It is type safe. This is wonderful. If you make a typo, it's not going to compile. You can use iterators, standard library, other fantastic Boost libraries with this, because these are all standard compliant or rather STL compliant containers, and it's efficient because once you load your XML and create a data model in your memory, now searching through it is just mostly pointer comparisons, even not that. If you index, if the implementation of data binding is nice enough, you can just index based on how it will be searched. So you're not going to do string comparisons as in a DOM, but in fact you will be just going through iterators much faster. And I have numbers to show how XML actually works better. But you have to spend some time loading the XML, however. This is great, but we lost actually something along this way. Quite a bit, in fact, I feel. Remember, XPath, actually, you can get the same query expression, find all author names in just a single line of code. So over here, XML data binding, this is the same example that I showed earlier. You wrote about 20 lines to do the same thing. Now, what did just happen in meanwhile? You started with some nice ideas. You want classes for your each XML kind of object, and now you're stuck with pretty long code, and you cannot anymore use XPath. Well, I'm going to show you how you can actually use this, but there are some limitations of that. But you want to stay completely typed. You don't want to pass like a string expression. So you're kind of stuck with this. Let's see if, so what we actually lost here, I feel, is we lost the succinctness of XPath, which is a XML processing technology, and this is not. If you think of XML paradigm, because you want to be more close to XML. So another thing that we lost is expressive power. So over here, I'm looking for names that occur anywhere in the XML. Like those could be book names or author names. I don't care, like this particular expression, I want to find name that occur anywhere in the tree. So you can easily write using this // which is very kind of idiomatic in XPath. You find names anywhere occurring in the tree, and even if tomorrow there is a publisher and publisher has a name, you are going to find those also. It depends whether you want that kind of surprises or not. It depends actually on your application, but that's the idea. Like you don't have to specify how to reach up to names. And the key thing I have changed here is these are actually nested. So this is a slight change I have made in the schema. Now catalogs can contain other catalogs. So that means name can occur anywhere in the tree and multiple levels. So that means you have to write basically a recursive program to arrive at those names in a data binding setting. So this particular function, get all names, is a recursive function, and more places you have names that can occur recursively, there will be more recursive functions. So you already lost this succinctness. Now you are also talking about complexity here. If you have multiple mutually recursive kind of elements, A contains B, B contains C, C contains A, you know, now you can imagine how tedious it can become, particularly if you have 500 types and you, you started looking at them just yesterday. You just downloaded this last schema. That's not a very good feeling, I think. And note I have used boost for each, trying to reduce the iterators. You know, it kind of looks ugly when you use just begin, and it's much smaller. Even with that, it's kind of a lot of coding, I feel. Are there any questions so far? I'm okay, you know, if you stop me during presentation, no problems at all.
So one thing I see is that what you may be complaining here is that C++ doesn't have very good object tree traversal functionality. Because if C++ had a way of saying accumulate for all elements of this collection, all elements of the contained collection, accumulate that, flatten that, then you could use the data binding and very succinct code to express this. So I think this is functionality that you could use a lot, and it's just not there, and it hurts everything, not just XML processing, although it hurts XML processing specifically.
That's absolutely right. So paraphrasing your question, if I understand it right, in general, a typed object model doesn't have to be XML. It can be actually Google protocol buffers. I'm going to tell you how this can be applied there towards the very end. As long as you have a typed data model, traversing that becomes kind of tedious with just object-oriented techniques. And that's why the talk is about multi-paradigm design. I'm going to use multiple paradigms offered by C++ to help simplify this problem. But there are more. It's not just traversal. We'll see in few slides. This is another very idiomatic way of using it. You know, star, a wildcard. Without spelling catalog and book, can you find name sequence? Can you find all names? I cannot even begin to think how you would do that in a typed setting. Anybody has ideas? You shouldn't type word catalog. Well, I have written it there, but book, let's say. And you have to arrive at names, the book names basically, in there.
You need to be 2 levels down in your loop that you have.
Right, but you shouldn't type book at all anywhere.
You would need templates, because you don't know the type.
Well, if you use templates now, that tends to be generic. So you need to know the getter. So that T must have. You have to effectively call get something. If that needs to be get book, it is part of the function name itself. It's not a parameter. It's a.
Yeah,
what's that?
You'd have to change a lot of stuff.
Right. So you know, I couldn't come up with this, and that's very powerful mechanism here called structure shyness. So this particular expression is kind of shy of structure. It doesn't want to commit what's there before name, and it just whatever there is, first 2 levels, I don't care, publishers, authors, books, doesn't matter. Just find, as long as it's a name at 3rd level, I want that. You cannot do that here. There are some other techniques maybe you can use. You can use cast it back to object maybe if your data binding tool supports that. Maybe you can use object.getChildren. You will get all the children, but they are all object, not a book or a author. So casting is inevitable there. So we are not interested in those because we want to stay completely typed as much as possible. Well, then you can also use XPath like a library. So this particular example, an XPath library can take a string encoded XPath expression, a little one right here. But you need all this boilerplate code around this. And that's not good because this particular loop here, that's while actually, is not standard C++ idiom. You know, it's kind of using iterator next or get node value. It's not standard iterator. It's not generic. You cannot pass this to a STL accumulator or STL algorithm. So the problem with this approach is not all tools support this, first of all, and then casting is again inevitable because author you have to cast it back to your object model author, then the iterators, and then the things that are outside XML you cannot write a query expression on. For example, I want to find books, I want to find authors of highest selling books. So this information of highest selling is probably another vector in your C++ program, not in XML. Now you want to filter your authors based on that. You cannot write any condition here at all because it's a completely separate domains, you know. So that's a problem you encounter when you use this particular approach. So I'm going to summarize what really went wrong. The problem really lies with its schema specificity. I mean, the approach that we had initially, like have a separate class for each type and have getters and setters for each member, is really trumping us here. Each class looks completely different. There is no generic, no commonality there other than maybe an object-based class. That's it. Completely different. And there are some other things that you cannot use visitor design pattern very easily when you use just XPath. But okay, you can probably use it with data binding if the tool supports it. So the question I ask here is, can we combine this type safety that's offered by data binding with this succinctness, this power of XPath? Can we remain typed completely, yet write really one-line sentences to get your data? And yes, I think it's possible. The solution that I'm proposing here is called LEESA, kind of hacked up acronym, language for embedded query and traversal. I spent at least an hour trying to find a better name, looking at turning these words around, couldn't do that. But anyways, this is what we are stuck with since 2008. So it's multi-paradigm. I'm going to use generative programming, object-oriented, meta-programming, and something very interesting called strategic programming to arrive at our problem, arrive at our solution. And we'll get these things in return. Structure shyness is possible while being typed. Compile time schema conformance. It will tell you if your expression is wrong. Then this is not schema or XML validation. This is your query validation. It's going to tell you whether your query conforms with schema or not. I'm going to introduce LEESA mostly by examples. I think that's the best way to get a hang of it. Here are the classes and the relationship between these classes. A catalog, a book. Catalogs are recursive. Here is an XML example of that. And note that I have different classes for price, country, and name. Now, in general, actually, a data binding tool will use an optimization it will encode prices, like a C++ double. It will not generate a separate class for it. Kind of sounds a lot of work, having a class for just a double. Even for a name, standard string. And country, maybe another standard string. Bear with me for a while. Let's have unique classes for pretty much everything in the XML. I have some approach where you don't need these separate classes for even the simple things. But once we are through with the concepts of using why we need these classes separately from built-in types, I can get to it and maybe answer that. Is there a question? Okay. Okay. So here's one example. The first example, XPath find all author names. So this is how the XPath looks like, and this is how LEESA expression looks like. So you load a catalog, which is basically the function generated by a data binding tool. You get the root, and all you do is you evaluate that in the context, and this is your query expression. Now see the similarity between XPath and that. All you write is catalog, right shift book, right shift author, right shift name. A couple of things to note here. These are all expression templates, not using proto. I'll get to that. These the regular parentheses, it's creating basically a default object of that. The expression is not really interested in this default object. It's really interested in its types. You're trying to say here, start with the catalog, find all books, find all authors in those books, find their names. And that's why the return type of this particular expression, when you evaluate it in the context of this particular root, is going to be a vector of names, and that's the first level, the simplest example of using LEESA. Are there any questions on this? Yeah.
So this catalog type and the first line and the last line is the same type, right?
Yeah, they are the same type, and they are generated by the data binding tool for you.
So
Yeah.
kind of looks like you now require catalog to have a default constructor.
At least in this example, that's right. It's not strictly required. I think I have an approach where you don't need this. The examples that I have, or rather the implementation that is currently downloadable, requires this because, as I said, the setting I started this with had default constructors for all the types. It was a data binding tool for our research. But yes, I think I have a solution that can circumvent that limitation. Question?
So I'm assuming the data binding tool is LEESA specific?
Good question. So the question was, is the data binding tool LEESA specific? It doesn't have to be, but you need to now create or generate, in fact, a layer that abstracts LEESA from the data binding tool. And as we'll see in the process, I have written a Python script that creates that glue code automatically from the generated code. We'll see how to use LEESA in general in even other data binding tools. So yeah, right now it supports 2 data binding tools. So maybe that can help you convince. Question?
I'm still about this default construction. Let's say catalog has, I don't know, 50 members each string. So does it mean that in this expression we'll create an instance that will, create a 50 members and allocate memory for them, things like that?
No, I mean it is actually just like sequential for loops. This is going to basically invoke get book operation, and just that.
So this is not really default construction, is it? I mean, because to me, if catalog is a type, then this expression will create, I don't know.
Let me paraphrase the question so it's recorded. So I think your question is, if it's a default constructor that's basically an empty catalog, and you cannot run anything meaningful, you cannot get out of it, is that?
My point is that if catalog contains a large number of members, then I'm trying to understand whether the actual instance is created or it's just a type expression.
Well, it will be created, but the optimizer should find that the data isn't used and just throw it away.
Question is whether the optimizer really throws unused temporaries away.
In this particular case, yes. The question is it going to throw away some temporaries that are created during the evaluation of this particular expression? And you're right, yes. Because the generality it supports, we're going to see that in a moment, it needs to create basically an intermediate vector of these intermediate types, books and authors, and those are passed to subsequent function objects. So what's actually happening here is, I said, this expression is really interested only in types, not the default objects. Basically it's creating composed function objects, and this particular expression is basically a unary function object that takes a catalog, returns name, and that particular vector basically. To do that in a very general setting, I need to create intermediate vectors for books and authors, and that is one place where its performance at runtime becomes slower than hand-coded data binding or code that is just data binding, because you can probably just avoid creating those temporaries while you code. Does that answer your question?
I still think that if the catalog type has a non-inline constructor, then that constructor will be called.
A non-inline constructor will be called for catalog.
Which means that all that memory will be allocated and things like that.
Oh, right. That's right. Okay, so just this execution of this, you're right. Yeah, the empty elements, empty vector will be created. That's why I have an approach where you can avoid creating these default objects. You can actually have basically static objects. I think That's what I have in mind to avoid creating these every time you execute it. But so far, these are actually the optimizations. So once we go through its core features, we can think of its optimizations. What are its bottlenecks? Moving forward, so how would you find all names recursively? Remember, we use // The names could be anywhere in a book or author, anywhere in the tree, because it's a recursive catalog. This is how you will write in LEESA, descendants of. So you are saying, again, this is going to be kind of pervasive in all LEESA expressions. You create a default object. Again, it's just interested in its type, not the object itself. And this particular expression, you are saying, okay, find me descendants of catalog, name, those are the descendants, and execute the entire thing in the context of root. So you did not specify book, author, country, anything at all. LEESA basically knows what those types are. It will go to those types, traverse through them, and find names for you. Yeah,
So this differs from the way this example was written in the website? The website has this evaluate.
Good question. So you can still write evaluate. Only difference is your second parameter will be descendants of this, the left half of it, and evaluate is just going to pass croot to it. Basically, if you see, this is a unary function object.
Yeah. So I like this one better because the other one had a lot of redundancy.
Right. I mean, I'll get to it why that we are. I mean, I'm kind of stuck with that redundancy, but this is going to evaluate lazily if possible, because you can actually pass this function object everything except this for later execution. Question?
In the previous slide, should the XPath example have begun with /catalog?
In the previous example, / is root, so that is the catalog.
Okay.
So I think when you write / without any axis, then it's by default means this is, you're looking for child book.
I think he's pointing out the XPath query that you've got there is not the same as the LEESA equivalent. You've got book author name text versus catalog book author name.
It is not equivalent, that's right. I mean, you have to start with the root object. After all, you are dealing with data binding, and the root is a typed object, and you need that somewhere to start your expression.
The point is the XPath query results in a collection of pure text, because you have the text function at the end.
Yeah, it's a list of nodes which contain text.
Yes, and the other lower one is just a list of the name nodes.
Right. I mean, name is the type that kind of wraps the
So if you omit the text parentheses at the end of the XPath expression, that will result in name nodes, which is then more equivalent to the return value you get from the LEESA expression.
So I think the question is, what is the text parenthesis doing here? If I could paraphrase it right. So if you just leave out text, it's going to give you a list of nodes that happen to be of label name. Now you need to do get text on it to actually get actual name, which is supported by XPath.
Which you have in the LEESA example.
Well, name can be maybe convertible to string, because it's a class that just wraps a name.
Okay.
Or you can simply just print with CR. I don't know. You don't do name dot get name. You have a name object with you. Moving forward. So this is a third example. How could you actually, without spelling the intermediate types, arrive at name objects? So here's a LEESA example. You start with catalog again, because that's the root of the tree, and you don't have to specify here anything. You can just say underbar, which is a LEESA predefined object in LEESA namespace. You just leave out it here and just put name. So that means you are interested in name objects only at the third level, and whatever comes in the middle at type level, whatever type, doesn't matter. LEESA is going to find those types for you and it's going to traverse the tree and find it. So again, this is a structure, another form of structure shyness. You can, like you wrote these wildcards, that's the parallel here. Are there any questions on this? Okay. Writing some predicates. So XPath allows you to write predicates like that. People, the authors from USA. In this particular case, there are a lot of things that I'm putting together. First, you can write larger and larger LEESA expressions by putting smaller ones together. So you start with the catalog. You find the descendants being author descendants. They could be anywhere because catalogs are recursive. Then you select some authors which kind of satisfy this predicate coming from USA, and then you, on that filtered set, you write name. I mean, you find names on it. So the idea here is you can compose different expressions together and write larger and larger LEESA expressions. Is there a question?
Can you go back to the
Sure. And yeah, that's a lambda. You could use bind, or your handwritten function object should be fine.
So in this expression you have to mention catalog twice, once as the root and once in descendants of.
Yeah.
Is that second one necessary?
The way I think, this is a good question. So the question is, why are we repeating catalog multiple times, at least twice here? I think the way it's implemented, this particular expression itself is a completely independent expression. You could use this without anything around it, as we saw in earlier example. To be a self-sufficient expression, this particular one, it's there. And for the entire expression, you need to have a first type where it starts looking for, and that's why it's repeated here. And in general, I had this feeling, yeah, there are some few places you have to repeat these types and kind of sounds unnecessary. But I think that's a side effect of having it composable, because this is separate, can be separately used. I think that's the best answer I could give you. So any more questions? Moving forward, XPath is, I mean, you can actually go beyond XPath with LEESA. What about so-called tuplification? I don't think that's a name, that's a valid word in English, but I'm just calling it. So you want to basically tuplify your members. You want to put together names and countries of a author. I don't think XPath offers you any way to do that. You cannot have a pair or tuple like that. But in LEESA you can do that. All you do is, again, you find descendants. I mean, these things are not necessary. I mean, you could use different expression here, but all I'm showing is its equivalent here. You could just use catalog / book, I mean, greater than book, greater than author, instead of using descendants. This is not necessary here. And members as tuple of, and you give us example tuple. Again, I'm passing in just the types to give it an example, and it is going to return a tuple of these things. It could be more than one type, more than two types, doesn't matter. The third thing.
Why does it return pointers?
Excellent question. So question is, why are these pointers? Now if you think about XML specification, you can have optional elements. So consider name is not optional, but country is. So internally the way it works, if you want to pair them together and you have, let's say, two authors, both the authors have name, but one author doesn't have country at all in it. Now you cannot pair them meaningfully because one vector is kind of longer than the other. How will you pair them up? So if it's null, that means the value didn't exist. So at least you have a way to both the vectors, I mean, that's the internal implementation. You don't see a vector of name, you don't get access to it. All you get is vector of this tuple, but you get the idea. It's basically kind of zipping through these pairs and kind of matches them. If it's missing, it leaves a null there. So, yeah, question.
Would you consider using boost optional for that instead of pointers?
Good question. So the question is again, can I use boost optional instead of pointer? I have been thinking about it. I think you could. One of the goals of LEESA is to map on multiple data binding tools and technologies, one being Google protocol buffers. Even that is possible. You know, it's basically the same approach. I'm not sure if, well, even in that case, I think you can use optional because GPB supports optional elements. So actually, I don't have a very good answer. I haven't tried that. So maybe we can discuss that later. If question?
Well, this maybe just a comment. This might be more useful anyway because you may want to modify those objects, right? You have your object world. You may want to modify it so you can write it back out changed, right?
Yeah, absolutely. I mean, these are pointers in the tree that the data binding tool built for you. Yes, that's right. Traversal. So you can use visitors with LEESA, which you couldn't use with XPath at all. Here's how breadth first traversal will look like in LEESA. And you want to visit, when you arrive at a particular type, say a book, you want to call visit book, you know, and do maybe a stateful traversal. Again, you can just compose expressions together. You just write a visitor. Visitor is a my visitor. Again, you cannot see my here. It's standard Goff visitor, and it's going to traverse like that in a breadth first fashion. No particular order. It's really what written by the data binding tool. It's going to visit all books, then all authors, and then all countries. And at this level, actually, you cannot figure out. You know, it's kind of making a sweep kind of horizontally. So you, unless you have a way to go to parent, you won't know if this C3 is coming from A3. You know, you won't know if C3 is even just second author of some other book. You know, but this is basically breadth first. That's one way of traversing. This is not all you can do. Now, just look at this. It's going to be a small change here. Now, if you put a assignment operator, right shift assign, it's going to change your traversal completely in a depth first fashion. So now, you take a book, you go inside its authors, you finish the entire whole tree here, and then go back to the next book. And same thing happens at this author because I have a right shift assign. That's just depth first way of traversal. Basically, these are nested for loops, actually. You could easily imitate that, you know, by nested for loops. You can have these 4 types. But it's very easy to switch from breadth first to depth first, and you can in fact combine these things together, no problem. Multiple visitors, so on and so forth. That's typed depth first. Question
with the breadth first version. If I do a selection on, say, books, I only want books that are, I don't know, cheaper than $100.
Okay.
Will it correctly propagate that selection to the children?
So the way you will do, okay, the question is if I want to filter books with whatever predicate, will that propagate, the predicate will be propagated or not?
So if basically if I attach a filter here that filters out book 2, will the breadth first, will in this expression, will the visitor ever get to see A3, C3?
So let me try answering your question with, you can have a select right between book and visitor.
Yeah.
And that means you did selection before you did visitation, so it's filtered.
Okay, but does it also apply to the later author and country?
Yeah, well, yeah, absolutely. It's going to work on the set that you got. Yeah, it's actually just as it reads. You know, because I couldn't write a really long expression. You read from left to right. Whatever it tells you, that's what it's going to do. It's find catalog book, select. You're going to prune it off, visit, prune it off. Author, country. Question back there.
Yeah, and the next slide, without the visitors using the right shift equals, can you control the order in which you get the countries at the end, if that's what you're collecting? You see what I'm saying? Like if if the result of this thing is that I'm going to collect all the C's at the bottom, breadth first versus depth first is going to, well, not in this case, but in some cases it might give you a different order. Can you mix and match those right shift and right shift equals to control the order in which you get the results back? If that's going to be the result of that even without the visitors being in play?
The question is, can I mix and match the right shift assign, basically breadth first and depth first operators freely to control the order in which countries are visited? Is that right? Yes, you can combine these expressions, operators, I should say. So maybe you want to do depth first starting from a book, but then do a breadth first for authors. So that means you will remove this assignment operator, and it will probably do, and it will do book, and it will go like A1, A2 and come back.
But I'm asking specifically if you don't have the visitor in play.
Okay, if we
an XPath type query, but you're changing the breadth first versus depth first with a different shift operator, I'm asking if that's possible.
So without visitors, so at least to me, depth first traversal without visitors actually doesn't make a lot of sense because you kind of visit, well, again, without visitors, it's like you are going to arrive at these type nodes in a mixed way. You will first go to author, then you go to country, then go back to author. So it's not consistent in terms of types. You don't group them in a single type. If I had, like in earlier case, all books, okay, I can find a vector of all books. Then all authors, I can find a vector of all authors. That kind of makes sense. But here it's going to, okay, first thing author, then country, then again go back to authors. You don't get actually a full list or a vector of one particular type. And if I understand the question correctly, actually, that's why the return type here is book and not country. Because you kind of visit them in alternate fashion, book, country, author, book, country, book, author, country, book, author, country, in that fashion. So is that even close to your question?
That's my question, but this is a small detail. We can take this offline.
Okay, sure, definitely. Question?
So what's happening? I'm having trouble visualizing what's going on in visitor because these are different types. What is visitor getting?
So the visitor has these visit functions, visit catalog, book, author, name, and depending upon your stateful traversal, those will be called.
I didn't see that up in the
yeah, it's kind of hidden in the corner. Again, it's cannot. I don't think it can be done in XPath because. Okay, yeah. Question.
I was kind of wondering about the visitor too, because it seems like it would be more idiomatic to use an overloaded function object.
In that case, I guess, yeah. The question is, it's maybe more suitable to use overloaded function object. That would be a templated member template. Is that right?
Or if you want to have, or you could use a template, or just have separate overloads.
That's perfectly fine. I think well, it's not implemented, but it's very close to the visitor semantics. Well, that's actually not right because visitor is going to do a dynamic dispatch. So I don't know, unless you make all these function object functions, well, the overloaded operators virtual, it's not going to do dynamic dispatch.
I guess I'm not quite sure why you need dynamic dispatch. But even so, you could forward from a dynamically dispatching wrapper.
Well, I think visitor is kind of for structured traversal. That's probably the best way of doing it. I think.
If you move your parenthesis over, say visit parenthesis catalog visit book, you're just overloading functions.
Yeah.
They don't need to be virtual, right?
Well, but in case of at least visitor, they will be virtual, and that means you can have different visitation semantics while keeping your traversal the same. Maybe your first visitor is a print visitor, and maybe the other, you can keep this the same, the traversal.
Why would they need to be virtual since you're going to supply, I'm going to supply the class written with the overloads that I need, right? And you'll call it from your framework.
You have to inherit from his, right? I mean, your LEESA is defining the visitor base class, right?
Well, it wouldn't need to, though. That's what I think.
I mean, yes, in this, visitors are not strictly necessary, but if you see conceptually, overloaded function object operator, it's just those visits without names.
I think what they're saying is you could use static polymorphism rather than dynamic polymorphism.
Right, and this is not eliminating static polymorphism at all.
Okay.
It's giving you both. But currently, it's not implemented. It uses visitors because, again, that's how it started. Okay, precedence. I mean, these operators have left to right associativity and everything. A pretty low precedence actually. You don't have to worry about that. You just write assignment operator if you want depth first traversal. It's creating expression template out of this is taken care of by LEESA using obviously standard C++ precedence rules, but you don't need parentheses. That's what I want to bring out here. So we saw these two expressions, basically breadth first and depth first traversal of a child axis. You're going down. We don't have to limit there. You can in fact go, is the same earlier comment, you can go other way around going parent axis. These axes are actually kind of important XPath notions. Basically axis unit traversal. It's kind of defined part of kind of lingua franca of XPath. And you can have a depth first parent axis traversal. I think that's possible. I found it kind of mind numbing when I kind of created this. Okay, I mean, it's a little change in expression. Depth first parent, you all tend to think depth first being going down, but I mean conceptually, why should there is no reason why this cannot be depth first cannot be done in a reverse way. It is possible provided you have access to parent object. Question?
Is it possible to mix the top to bottom and bottom to top?
Absolutely. All you do is just stitch it together. Left shift, assignment, right shift. You just.
Is that your worry that you get stuck? You're going down and then back up and then down.
I'm just wondering if you could run into any weird issues where it doesn't, where it's syntactically possible but doesn't make sense.
I probably won't. The question is, can you mix child and parent axis and this traversal freely? I don't think there will be problems because you create a temporary list or a vector, and that's what goes to the next so-called function, to execute. Yeah, so let's move on to, I'm going to kind of speed up a little bit because I haven't even started with how it's done, and that's kind of very interesting stuff. So you can find members, using auto, you can name these because they're actually just function objects and unary function objects to be precise, and they are executed in just one particular root or somewhere in the middle. So you can have, you can name them, that's what I'm trying to say here. Now this is interesting. What if you want to say, I have this visitor, I don't care if there are 500 types or 1000 types in this particular tree, just visit everything. Just visit everything from start to bottom in this XML schema, and so you can do that. All you do is you specify the root, and you specify basically two strategies. Okay, while you visit it, call this particular function visit catalog, and when you leave that, call leave. So now you have a control over depth of traversal. So as it is drilling down your tree, it's calling visit as it goes down, and when it comes back up, it's going to call leave on its way back. So now you have a sense of depth in your traversal, and that's going to be completely automatic. By the way, if you write this on a 300 type schema, you can easily have your dinner by the time it compiles. We will go back to that. Compile times it later. Question?
So you're leaving out the signature, right? I mean, the visit is passing you a pointer or something to the object.
Yeah, just one reference, usually by non-const, because you may want to modify it.
Right.
Or a pointer. Again, the key point, you did not specify any type at all. There could be 500 types in your schema. It's going to visit all of them in a typed fashion. So one way of looking at LEESA is what it is and what it is not. It's not a XML parsing library. From the examples, you have probably figured that out by now. It's a query and traversal library. It does not validate XML files. It actually validates your XML query against your schema, not XML document. It does not, well, now kind of sounds funny, does not compete or replace XPath. XPath is way more powerful. It has, it's basically meant for XML programming. I have to live with what is possible in C++. But at the same time, it goes beyond XPath, like visitors and some other things we discussed earlier. It does not resolve XO impedance mismatch. A great paper by Dr. Ralph Lamel. Basically, it talks about data binding cannot reflect with 100% fidelity of XML. It kind of leaves some weird things, anonymous complex elements, regular types, those kind of things it leaves behind. It's a great paper. It doesn't resolve that, but it simplifies typed XML programming because now you have this succinct way of finding information. It's a DSEL, and I think this idea can be applied anywhere where you use data binding. One example being GPB, Google Protocol Buffers. So I'm now going to talk about LEESA in detail. I have about half an hour, right? I think I have to rush through these slides to some extent because these things are also very interesting. Performance, runtime, as well as compile time. So the process of using LEESA is just like before, but now we generate more data, or well, more code than just object-oriented code. So there is a thin layer. We'll see an example of that, so-called type-driven data access, because everything is built on types, and there is static meta information. This is basically the kind of the magic behind LEESA. The schema is represented in a form that C++ compiler can understand. And now you have all this power of metaprogramming. Entire schema pretty much. It's done using MPL. And now you can actually take optimal decisions, and you know what is contained inside what. Basically you can traverse this XML graph, which is represented in C++ using MPL. And that's where it knows the types. And that's why this information is generated from schema. And now you use access-oriented expressions and recursive traversal to actually create your application. The extended schema compile itself is actually multi-stage process. As I said, it started as a research project. So basically, I used Oxygen to parse the header files, and it creates an XML representation of that code. I don't go to parsing C++ code. That's just horrible thing to do, I think. So Doxygen does a great job. I get XML representation of that. And this metadata generator, this is all packaged up in a script. It generates all these three things for you. Visitor declarations, this thin layer, and the MPL basically information. Ideally, this would have been great if the schema compiler could simply generate that. These three things are actually very small and tiny compared to what schema compiler already does. These are very kind of thin layers, pretty straightforward. I took, I don't know, about 10 days to do kind of functional script for all these three things together. Pretty, child's play for those who are already developing schema compilers. So here's how the type-driven data access looks like. The problem was each class has a different interface. We want to fix that. These are basically children overloads for basically all the types, pretty much all the types. And I pass in each pair, so these are all unique because these pairs are unique. And for this pair, I call c.getBook. So basically with that now, this lack of genericity is back to me because I can pass a catalog object and say, okay, give me all books, provided I know the books are contained in catalog. It will basically map down to this particular function. It will return a vector of books. Go ahead, question.
What about an XML schema where one element has two named sub-elements of the same type? How would that work?
Excellent question. The question is, what if XML schema has maybe 2 even different labels of same type. This must be worked around. One way is to create a separate type for each label that you have in XML. That means even the first name and last name. Actually, I have the next slide just about that. So give me a minute. So the idea is you hide this schema specificity behind these children overloaded functions. So provided you know the type you're interested in, you can just call children, you're going to get that. And this works only if all these right-hand side things are unique. The pairs are unique. The problem just talked about is, what if the first name and last name are both strings? So this particular overload is now ambiguous, because obviously compiler cannot distinguish between these two, which one you are calling. The first solution that is available now is to force data binding tool to generate different types for even the simple types like strings. So I have a script that converts that schema into this by adding this restriction. So now you will have a first name class that inherits from string. You have a last name class inheriting from. Excellent. So the comment was this may not work in practice because data binding compilers, as I said, are really smart. They do a lot of stuff and they can figure out this is, you are trying to trick them. They'll just optimize this away and use just string, which is a great point. So that's why I have another solution. Well, now, okay, so this is how the mapping works now, because now you will get first name and last name as distinct classes, and then LEESA should be happy. Another solution is, again, not implemented, but to wrap these types, basically string, to make kind of unify them, not unify, uniquify them, maybe. You just a template here that takes an integer. So now I have a type def, unique type string 1 is first name, and unique type string 2. So now we have 2 different types for actually just the string. So somehow there needs to be a way to extract a string or the nested type out of this unique type template. So I think that can be done. Question?
You probably want to not use 1 and 2, but use a struct called first name, maybe inside of a namespace, but an empty struct called first name that you use as your uniqueifier, so you don't have to end up using the hints.
Well, yeah. Okay. The comment was, instead of using template-based approach to actually generate a unique struct.
Exactly the same, but my gut instinct is that you'll find problems with using the 1, 2, 3 for ints, and in place of 1 there you would use an empty struct that is named, that is called first name as your uniqueifier. Then you don't have to worry about keeping track of how many I have and what number I'm on.
But then eventually that needs to be mapped to the underlying information, that being the string.
Sure.
So either there needs to be a, I don't know, free function to convert that, or something like that. So okay, so that's one limitation I think can be worked around. So here is how the schema is represented using MPL, and this is kind of the heart of LEESA. So this is the schema. It's a specialization of schema traits for catalog, and says there are some children and those are book and catalog. So now you kind of query at compile time, tell me the books of catalog, and it, okay, book and catalog, because catalogs are recursive. Now tell me the books of, sorry, children of books, okay, name, price and author. So you can iterate over them at compile time. I mean, this is all done by LEESA. And those types that do not have any children, just kind of terminal, map here, it's just empty sequence. So LEESA meta programs are going to use this information to, if you start with a catalog, using this schema trait, which is automatically generated by the Python script, now you know what types are contained inside a catalog, which are book and catalog. And you can just keep doing that again and again till you go to the leaf kind of element, which is, say, price. Question?
So this is starting to seem very similar to the things that Boost Fusion does with its adaptation layer for structs.
The comment is this is very similar to Boost Fusion adaptation. Unfortunately, I'm not familiar with that. Maybe you can. I think is it the structures are kind of the elements of structures kind of you can iterate on them. Is that what you're referring to?
It allows you to iterate over structures.
Right, right. So this is similar to that. Yes. Yeah, that meta information of what is contained in what is available, is made available somehow. There is more, however. The earlier one was just child information. Now you can use that information to find out at compile time whether maybe type A contains some type B, you know, way down the tree using just closure. But that takes a lot of time at compile time. So the approach I took here is basically create these pairs for all the types basically. Is descendant. So as long as, let's take this second line. So book is a descendant of catalog. Somehow you can reach from a catalog to a book somehow. That's what, and it's true. Maybe let's take another example. You can go to country from catalog somehow. That's what it's trying to say. So you can reach this particular element if you start digging inside a catalog, and similarly for books and authors. But those that are not reachable map to just a basic, the general template is descendant. So everything else is false. So if you have really large schema, yes, there are literally thousands of is descendant specializations that tell you at compile time whether this type is reachable from this type. And you may have guessed this is actually used to optimize traversal. If I know that, that's probably the next slide. Anyway, if I know that this type is not reachable from this structure, I won't even bother looking at it. I won't even call get whatever on it. So you can optimize traversal based on this type information. Oh yeah, that's the one. So you want to go from catalog to country. So your first question you ask is, okay, is that descendant first of all? Yes, you can go there. So that means the first level of check is kind of done. And then you find, okay, now let me go in book and catalog. Then I'm kind of going to rush through these slides. Just pay attention to this particular diagram. Then I check, is country reachable from a book? Yes, it is. And then I find the children of book. Then I ask question, is country reachable from name? It's not. Is country reachable from price? It's not. So that means I don't even have to do a get on those. So I don't, you don't have to do name dot get country because it's not even going to compile. So why even bother, you know, calling that? So only thing that is going to work is country is reachable from author. So that's the only function that will be called, and everything else, it kind of knows, it's schema aware. It knows your schema. It can take optimal decisions based on your schema. And the last part is name. Is there any question on this particular? So how is this actually implemented? Because, you know, these are schemas, user-generated schemas. So we don't know what's actually in there. The approach to generalize this, you know, something that can be shipped as reusable library, I think strategic programming is something that is key to achieve that. It started in 1998 actually as a term rewriting language called Stratego. Why am I using it? It allows LEESA to be generic. It is schema aware. At the same time, it's generic. It can work on any schema. It's it can handle recursive schemas. Again, that's because I'm inheriting these properties from strategic programming. Reusable, you can have, basically you can ship LEESA as a reusable library. It will work with any schema. And it's composable. You can have larger and larger, rather complicated recursive traversals from smaller elements. And these are basic combinators in terms of strategic programming that allow you to create these nice traversals. I'm going to just do a depth first traversal of entire tree as an example here. I'm going to skip these details. All I'm trying to do here is arrive at those combinators. But instead of that, I'll show you how it actually looks like, visually when it does a traversal. So if you do standard strategic programming, then which is kind of type unaware, so these are all just circles, there are some nodes. It doesn't know which type is contained in what. It's just going to do all depth first traversal. It's going to visit every subtree and going to find, are you here, are you here, are you name, are you name, are you name, no. And even if it says no, it's going to drill down. This is obviously suboptimal. If we have information where types are exactly located, for instance, I'm looking for some price elements. I know that prices are definitely not inside author. So I want to bypass that. And that is what is possible using is descendant information. So you can bypass these, and your schema, your traversal is type aware, schema aware. So this is a big advantage over regular strategic programming because you can take optimal decisions based on your schema information. So you can again use this same information for conformance checking. If your expression is kind of doesn't make sense in the context of schema, I want prices inside author, is going to say no. This was developed in context of actually C++ OX concepts, so there are still parts of code that, so error actually ends up being in the concept, and there are some details. We can take those offline if you're interested. So the different kind of errors that are possible. So books don't contain other books, so this is going to flag an error. Sorry, parent-child concept is not. Cannot match it. Books are not contained inside books. Here's how a error message looks like in Visual Studio 2010, about 35 lines, I think. So error ends up being in level descendant kind concept. It's saying that if you start with this parent kind and you want to go to country, well, okay. I have a different example here. I'm trying to say, okay, find country objects exactly one level away from catalog. It's going to say, sorry, there are none there. You need at least 2 underbars. That means 2 wildcards there. And this is the error. It's not going to suggest you how many you need, but it's going to tell you that something is wrong with your query. These are again some details of expression templates. I think I have another 15 minutes and 10 more slides. Okay, maybe I can touch briefly upon why I don't use Boost Proto. So this is how a LEESA expression looks like. Again, chain expr, it's combining them together. So correct me if I'm wrong. A Boost Proto expression, this particular one will not work because catalog is not a Boost Proto terminal. So it won't kick in its expression template mechanism. But I think even that can be worked around. Although ideally I really want the types that data binding tool generated for you to use this directly. That's how it started. So unless you wrap this somehow around, make it a Boost Proto terminal, it's not going to kick in that particular procedure. And then I don't know if Boost Proto, even if you make that to work, is this expression going to be a unary function object? Because I want to pass this to a STL algorithm.
You can, of course, make it into a unary function object because that's exactly what Phoenix does.
Okay.
Which uses Proto.
I see. So by default, this will, not by default, right? You have to probably have to do something to make it a unary function object.
Yeah.
That's great. That's good to know. Everything in LEESA is a unary function object. Everything. It's basically a giant factory of creating function objects and composing them together. So you start with a catalog, and get children is going to return you a vector of books, and then you take that, you pass it here, you get a vector of book. Sorry, yeah, you pass in here. Is that wrong? No. Okay. So you pass vector of books to this get children, and you will get a vector of authors for every book in the vector, and that's how it continues. And you can compose them together because you know its parameter type and return type. As long as they are consistent with respect to the schema, it's going to combine them together just like invest similar to bind and probably Phoenix. Of course, details definitely vary, but conceptually they are all function objects. This is again a somewhat simplified code. The left and right are could be any expression. It could be LEESA expression, and that's how it generates types. I think I can skip this in interest of time. Another expression that uses depth first traversal are kind of somewhat different, but again, this is created first, evaluated first, so you get this tree first and then it's kind of composed with the other tree. There can be larger expression here also, but that's how it overall looks like. So yeah, it is basically systematically composed unary function objects. That's where you get this succinctness and composability. Excellent. So now this is the last part of the talk. I'm going to talk about what you will gain and lose if you decide to use LEESA. 87% reduction in code. These are numbers I got from about 300 types in the schema. Again, visitor based. Several traversal patterns, so to speak, were replaced by, these are the original lines, and they were replaced by LEESA. A single loop, just a single for loop. Not a tremendous reduction, but okay, still some reduction there. Two nested loops, maybe sequential loops, as members, you want to visit members of a particular element, a complex element. So you will write basically 5 for loops. Instead of that, you will write a members of here. The most interesting one is leaf node accumulation, particularly if you have a recursive schema which contains A contains B, B contains A. Finding descendant, you are going to write a lot of code depending upon the level of recursion in it. It doesn't matter how much recursion is there in your schema, it's always going to be just one line. Descendants of A, B, that's it. And you just execute it in the context of some A. It's always going to be single line. And that's why, well, it kind of shows 4 because it's basically indentation actually. Evaluate, context and everything. This is where you get the biggest benefit of using LEESA. Unfortunately, it's kind of slowest for compilation for that. Of course, it is going to do tremendous amount of stuff for you. It is going to figure out your schema. It's going to find where the elements are looking for, where they are. Is going to go to them optimally. You cannot. This is probably optimal, except creation of temporary vectors. In middle, it's going to do optimal decisions as far as the tree traversal is concerned. And there is no reason you may skip or having a bug of forgetting a particular branch. That's not going to happen because code is automatically generated. Here's the runtime evaluation. The red line is handwritten data binding code. So you can optimize away creation of temporary vectors. It's about 2.5 times slower. Descendant axis, green is a descendant axis. There is slight difference between child and descendant. These expressions were about just 5 types actually, because this is a runtime performance evaluation. The very simple catalog exam, that's what I took. Just for comparison benchmark, I also use libxml just using C and XPath string expression, and eventually with text/text. It's actually slower than data binding. That's because you don't have to do string comparison. I think that's the answer. So yeah, it is somewhat slower because of those things. But with C++ OX, R values, move semantics, chances are you can eliminate some copies, but still there will be overhead because eventually you are going to create intermediate basically containers. That overhead I don't think can be eliminated. Question.
Why aren't those like lazy ranges of begin end iterators, and you don't?
That's a great question. You have remaining question?
No, like just they wouldn't have to copy big giant vectors all the time. It would just more a lazy evaluation and probably like some kind of range concept that pointed back.
The comment is maybe instead of copying the vectors, can use ranges, and copying ranges would be much cheaper than a large vector. I haven't thought of it yet. It's probably doable, but I think you have to kind of remember what each range is at each level, you know. Like, it's a tree, there are multiple vectors in the middle, so you have to, the number of ranges will go up, you know, as you drill down the tree. There is a vector of books here, there's vector of books here, vector of books here, vector of books here. That means you have a range here, range here, range here. You go down further, there are again multiple authors. So I think there will be an overhead even maintaining the ranges. So if I understand right.
Yeah, I don't know. I get this feeling that lazy evaluation would.
There is, towards the end I'm going to talk about lazy evaluation. Actually, what if we could replace everything with iterators? More like coroutines. It's not implemented, but probably doable. So that's something can be used. Okay, so next is really interesting, the compile time performance. The red line is, okay, I should say, the schema actually had about 300 types in it, and 4 types were recursive. The code, I created about 5 expressions, 8 levels deep. So schema had maximum, without recursion, about 8 levels of hierarchy. The difference in compilation for object-oriented code, just data binding, is pretty much nothing. It doesn't change. Even if you have more and more, expressions or other traversals, it barely impacts it. But here, of course, the worst performer here is descendant axis, because it is going to do a lot more work for you. As I explained earlier, the types, finding types, optimally going there. Some part of this, I think this part is basically parsing LEESA itself, is about 5-6K lines of code, a whole bunch of macros in it, but even with expansion, probably not over 10,000. The more you ask LEESA to do, like finding descendants, basically more lazy you get, is going to take more time to compile. And that's why with single expression it's about 13 seconds, 5 expressions, all descendant axis, so is about 26 seconds. It's not terrible, but I think in industrial setting it's probably go up. I mean, it's at least linear, we know that, but not too terrible. Any questions on this? Yeah, go ahead.
One, can this framework be shifted over to JSON, to parsing JSON?
Provided you have a data binding tool that generates classes and things for parsing, reading and writing JSON. For Google protocol buffers, for example, it's a data binding technology. You describe your schema, you get your classes.
Which protocol?
Google protocol buffers,
okay.
GPB in short.
Yeah.
So yes, it's applicable there, but the code generator needs to be adapted for that particular data binding tool, because the function call conventions are different. Some tools use get underbar something, get foo. Some just use foo, capitalization, that's different. So some adaptation may be required. I mean, definitely required.
Okay. So another,
yeah.
How does this relate to Xfilter, Yfilter?
The question is, how is it related to Xfilter, Yfilter? Unfortunately, I'm not familiar with that.
Okay.
Maybe we can discuss offline. The child axis, however, is actually much better. Its slope is flatter, and really speaking, it's not doing much in terms of schema conformance. I mean, it does check whether you are a child or not as you write your expression, but it's really not doing complicated metaprogramming during compilation. The metaprogramming really happens in descendant axis when you don't specify types. I had much higher hopes with variadic templates. I thought, because I'm using MPL, I created equivalent variadic vectors, MPL vector-like things. I was expecting significant improvement in performance. I don't know, it somehow doesn't happen. It's about 20% better, and its slope, it's about the same. So anyway, that's what I found out. I don't know, I used variadic templates optimally or not, but that's what I found out. The third graph I have here is the overall compilation. So the earlier graph was a single file having 5 LEESA expressions. That means the other stuff like compiling your data binding code itself, the object-oriented code, and so those object files are already ready. All it does is, this is what you will tend to do as a developer. You will change a few things in your main program and you will recompile to test it. That means the code that you did not touch, the object file will be reused, and to be just relinked. So this is what it's telling you. So you will wait this much time during your successive compilations, maybe every minute, every 5 minutes, something like that. Your nightly builds will take this much time. It will start from a clean slate. It will generate code from XSD schema to the C++ data binding code. It's about the same on all platforms. The interesting thing is the time it takes to compile the rate is basically the time it takes to compile just plain data binding generated code. No LEESA, no magic, just data binding. It's kind of pretty big chunk of compilation. The green part is just parsing LEESA library, about, I don't know, 6,000 to 10,000 lines of code. Purple, I think, yes, that takes variable amount of time depending on compiler. I think that significant difference in G++ 4.5 is because it's much better at looking up specializations. So remember is descendant, there are almost like on a large schema about thousands of is descendant types, specializations. G++ 4.5 is really good at looking them up. Others not so much. So, but still if you compare compilation time, these are about 5 expressions for descendant axis. Yes, they are all descendant axis expressions. So if you look at the overall compilation, it's not terrible. That's what I feel. The 79 seconds, it's something funny, I don't know. Visual Studio 2010 just sits there generating code ... I think it's generating binary code at that point. Other compilers don't seem to do that. So you kind of see a shift here, but there is no, this is just, I think, linking and something like that, I guess. So, but that's the overall picture of, basically nightly builds of 5 expressions. Excellent. So C++ OX. I thought, I still believe there is a lot to gain as every generic library can gain from C++ OX. Readability can be improved significantly because using lambdas now you can, for filtering, you can just simply use those lambdas to filter out when you select. You can use sorting using your own predicates or comparators. LEESA actions, that's where lambdas will be used. A static asset for better error checking and error report. You can check whether your expression conforms with schema or not, and then print out that error much more in readable fashion. Auto for naming LEESA expressions, you can pass them around. You can get really large expressions and compose them together. That's possible using auto. I think alternative is to use boost function. But then I think you'll need to spell out little more types, at least because all of them are unary functions. At least you need to specify parameter and return type. But that can help you reduce your typing. Reduce your need to know the types. Performance. I don't have performance numbers using R-value references and move semantics. I think significant improvement can be obtained. The reason I don't have it, because the underlying data structures that I'm using, particularly XSD, the tool XSD from Core Synthesis. Boris was sitting right here. I think he's there now. I don't think those containers support move semantics. So unless you have library that supports move semantics, you cannot have top level elements, top level structures that can use move semantics without any cost. So if that's right, that's why I couldn't do those. Variadic template, as I said, there was some improvement in schema performance, schema checking, and overall execution, compile time execution. It supports actually large number of types. Without variadic templates, LEESA right now support, I have tested at about 200 types, like one parent contains 200 different types of children. I mean, that is definitely outside, the default of MPL vector, usually 60, I believe. I mean, it's just a matter of creating some macros, I think. And implementation, yes, LEESA's implementation can be again simplified in C++OX using trailing return type syntax because it's all hand-coded expression templates. I think I don't have to know those types as a developer and few other things. So I think C++OX has a lot to offer to improve any generic library. So the goal in future is, if there is enough interest, my goal is to make it part of Boost. I think it would be an interesting library, XML programming library, not parsing, and it has very different approach compared to what's out there, like DOM, just regular data binding, and SACS. It's possible to extend this to Google protocol buffers. Anything that is schema driven and you generate C++ classes, it can be applied with few things that are still need to be tested in the field, like unique types and those kind of things, but as it's tested more and more, it can be done, I think. Because of the higher level of abstraction in LEESA, it's, I think, possible to obtain transparent parallelization. Because you are no longer telling how to find, you're not telling how, you're just telling declaratively, okay, find me all these descendant, name authors, done. It is now possible for LEESA to optimize or use multiple, if configured that way, to fan out multiple threads and put them back together transparently. Because you are at a much higher level of abstraction, you are not writing for loops yourself. So I think it is possible to extract much higher performance. Yeah, go ahead.
What XML data binding tools is this compatible with right now?
It is code synthesis XSD. Okay. There is one more which is not used a whole lot, called UDM, Universal Data Model, which is kind of stable, but mostly used in research, where the institute I worked at.
The core synthesis one, is that a proprietary software product?
And there is a, I think, open source license with some conditions. Okay. It is, yeah, it's both. Commercial license, and maybe Boris can help me with that.
So this would sit on top of that, right?
Yeah.
You don't need this component, and that's doing all the schema about the parsing, schema validation,
right,
and that sort of thing.
Right. The question is, who is doing the XML parsing itself? It's the data binding tool. This is actually just extraction of information. That's it. Coroutine style program. This is what I mentioned earlier. Pretty much everything in LEESA returns a vector, or basically a container. What if you are interested only in the first element of it? The remaining million elements that it searched for you in the whole tree, you are just going to throw them away. What if you could have similar syntax, but actually obtain a kind of composed iterator that you just do plus plus, and if you find the first element and you just stop searching. Basically, motivated by coroutine style programming, you can do lazy evaluation. It's not supported. I mean, I think this can be done, but far from telling you actually how easy or difficult it will be. But given the high level of abstraction, I think it's doable. And XML literal construction. So far we saw just querying data. So what's already out there, you extract it out. What if creating XML itself? So I believe VB and even Link supports literal construction. So you can have your C# program, it will check against a schema. I'm not too familiar with it, but I think it's possible to write very small XML snippets which will be compared against schema. Maybe it's possible because eventually you have this schema information in compiler, so you can use that. Maybe variadic templates would be particularly usable in this particular case, because you can create really large XML literal, in the program. So yeah, the conclusion is, I think it's possible to solve these XML programming concerns. So again, if you think about XML programming as a, if you give it the due respect kind of, it's full-fledged paradigm. You have to deal with representation, how do you access the data, and how do you traverse it, and whether you do schema conformance checking. There are these details of traversal, breadth first, depth first. All these things actually can are possible using multi-paradigm solution that LEESA offers. You can combine these in various ways to solve this problem. So that's about it. If you have more questions, I'm happy to take them. Yeah?
I was just curious how you would go about applying it to your own data structure.
Right.
You mentioned that.
So yeah, the question is how can this be applied to hand-coded data structures? Yes. So as long as I think you have somewhat predictable data access pattern, most data binding tools generate it in a very consistent way. If that has been followed in hand-rolled classes, it's possible because the Python script that generates this schema representation and everything works directly on C++ classes. I mean, not on schema. There is a reason behind it. If you want to support multiple data binding technologies, then that means there is RelaxNG, there is Google protocol buffers, it's different schema, then Apache Thrift, then maybe hand-roll classes. The common thing here is they are all C++. Their schema language is very different. Running after schema, conforming full schema or parser is a humongous task. Not all data binding tools support entire XML schema specification, just gigantic. Much more tractable problem is to parse C++ code, not yourself, but leave it to Doxygen or a tool that can do a reasonable job at it. I'm sure Doxygen has its limitations, but I think it's still better than parsing XG schema. We are running out of time, or you have a question?
I have a question.
Okay, question.
Actually, I have a comment.
Sure.
And that is that one of the nice things about the last year or so is that a fully featured, fully compliant C++ parser has become available as a library.
Clang,
from the
CLang.
LLVM project.
And
is that I've found that there are a bunch of C++, complicated C++ constructs that Doxygen just doesn't deal with.
Okay, that's right. So the comment is Clang compiler, which is basically a library approach for building a compiler, C++ compiler. That's a great point. It can be used, but I still, I anyways need access to C++ code because the visitor declarations actually need to go in the C++ class, the visit. Now of course you can just pass a parameter, okay, don't generate any visitor functions and it won't be generated. That's definitely doable. That's what LEESA supports now. But yeah, something to think about.
Although, Clang has the rewrite the module which supports that.
Excellent.
Supports adding functions.
Rewrite module. Yeah.
How scalable is this XML processing? If you start moving up to data mining applications where Hadoop typically a massive number of nodes, is there a performance curve? I mean, is there some sort of exponential where there's a need where things look great and linearly
so you're talking
all of a sudden it starts to fall apart, or
so the question is how scalable is this approach? Is that with really large for data mining? So that means there is, I'm assuming, pretty large schemas, about 1,000 types, and really large data.
Yeah.
So for runtime, so the earlier graph that I showed, although it looks exponential, I kind of missed the important information. The x-axis is also exponential. So right here, so 5,000 name elements in XML, and actually I missed another important. Anyways, good that you asked me. So this particular scheme, the XML was about 160 megabytes. It had 320,000 name elements in it, and just to parse and validate and create a data model in memory took gigantic amount of memory. Parsing took 33 seconds, and running one query, descendant access, took 0.3 seconds. So it's the bottleneck here is parsing, validation, and construction of object model than the query itself. I mean, this is a pretty large size of XML, I think. So I think shortly your answer to your question is performance really depends on how large your XML is going to be.
Okay. At some point you're limited by, you need the whole XML sucked into memory.
That's right. That's kind of a limitation of data binding tools, if I understand them correctly.
It's not like
Yeah.
sex, one pass, it's more like the done, you need the whole thing.
Yeah, I think you could get rid of that limitation, but it'd be some work.
You wouldn't really use XML for, that large data mining. It's just, there's just too much overhead in there. It's great for, it's good for descriptive data, but when your goal is mining huge amounts of data, there's just too much overhead there.
Right. Well, typically we use JSON, at least to get away from XML.
But even for
Yeah, but for large scale, yeah.
Really? You're using
No,
JSON?
JSON, no, for iPhone stuff and iPads, where it's just faster to download and parse than XML. We found it empirically and.
Oh, I thought your question
well,
was more
two
towards
separate things,
Hadoop type stuff.
Yeah, two separate things. There was the JSON part, but on the large scale. The thing about the large scale data mining is that sometimes you have no control of the data formats.
Yeah, but you'd flatten, if that's what you're doing, you'd flatten that data and put it in a form that you could easily parse and analyze, rather than leaving it in a form
I see what you're saying, yeah, okay.
Any more questions? Awesome. Thank you very much.